Most lectures on neural networks start with a deep dive into the biology of a neuron in the brain, and this drives me absolutely nuts. For one, most data scientists aren't biologists, myself included, and if you ask me, the data science field isn't really lacking in trivia-winning encyclopedic mansplainers. What it needs more of is compassionate and humble engineers willing to accept and acknowledge expertise beyond their own, like biology, for example. But far worse is how much this misleads people into thinking that neural networks have the potential to function like a human brain, which couldn't be farther from reality. Using no math beyond addition and subtraction, I hope to show you in this video that a neural network is just a simple mathematical process in the same way that long division is a mathematical process. This is how I think about neural networks, in a super accessible no math intro for beginners sort of way. The whole paradigm of machine learning or data science is capturing and quantifying relationships between different things. Some things are related and some things aren't. If I'm trying to figure out, for example, the biggest predictors of academic success, I first have to figure out how to quantify academic success since it's a pretty nebulous concept. I can start by scoping academic success as being defined by GPA. So my next step is to figure out what factors influence a student's GPA. I might look at things like time spent studying, extracurricular activities, household income, number of absences from school, etc. We intuitively know that these are all related to GPA. Data science and machine learning tools help us quantify exactly how much each of these factors influences GPA. For example, the output from one of these tools would be a mathematical formula like this one: number of absences divided by 2 plus study time times 2, etc. equals GPA. If you plug in a student's household income, extracurricular, study time, etc., the promise is that you'll get a number that is really close to their actual GPA. But the accuracy of these machine learning tools is completely determined by the quality of the relationship between each of these factors, and in this case, GPA. Things like the weather at the top of Mount Everest or a student's hair color, we intuitively understand as being unrelated to GPA. And so there does not exist a mathematical formula of weather or hair color that can accurately capture GPA. So when we set up a data science task, we would like to collect data that is relevant to this task. The factors that influence whether a student will pass an exam are different from the factors that determine whether a tumor is malignant or benign, which are different from the factors that determine whether a credit card transaction is fraudulent. Turns out, finding what factors are best for a given task is one of, if not the biggest obstacle in machine learning today. A neural network is not only a machine learning tool for quantifying relationships, it's a tool with a promise to automatically extract the right factors for the task. For example, let's say you're trying to determine whether a student will pass an exam. Used to be, you had to use things like reasoning, or common sense, or even domain expertise to realize that passing or failing might depend on things like their current GPA, the length of the exam, the amount the student studied, their well-being, etc. With neural networks, you can pass it all the data you have, relevant or not, and it promises to find factors that allow it to best predict whether a student will pass an exam. I know what you're thinking. What could go wrong? Fair enough, but it's not totally unreasonable of a thought. Information, although not explicitly present in the data, may still be there, hidden under a combination of factors. For example, let's say we don't have GPA in our dataset. Maybe we forgot to include it, but it's clearly important to our task of figuring out whether a student will pass or fail an exam. But if the data has information like study time, hours of extracurricular activities, household income, number of absences from school, we can probably guess at their GPA because remember, we know that GPA does strongly depend on these factors. So even though you may not have a given factor explicitly in your data, as with GPA in this example, it's actually very much there, hidden under a combination of factors. A simpler analogy would be that I could say, wow, this oven-baked egg flour sugar butter mixture looks delicious. Or I could just say, wow, this cake looks delicious. Before neural networks, data scientists had to manually comb through the data to try and extract hidden factors that could be relevant to the task. Neural networks promise to uncover these hidden factors that are relevant to your task automatically. Basically, you feed it your data and it just works. Or at least that's the idea. The rise in computational power has made it a highly accessible convenience to simply feed in your data to a neural network for it to magically extract information toward a specific predictive task. But how does this actually work concretely? What is a neural network? A neural network isn't an app or a product, it's a tool. It's a mathematical process. Let's pretend for a second that an alien, new to planet Earth, is studying human behavior. They're particularly interested in trying to figure out what exactly determines whether a person can or can't legally drink. Don't ask me, I don't understand alien priorities either. They eventually realize that age seems to be a big factor. So they go around asking people for their age and whether or not they can legally drink. They collect all this data in a dataset that looks like this. What they want to figure out from this data is what exactly distinguishes people who can legally drink from those who can't. And there are many ways to go about it, and you can probably think of some off the top of your head right now. The whole field of data science and machine learning is full of various tools to do just that. But how do neural networks go about it? Notice that if the alien guesses that what distinguishes people who can legally drink from those who can't is that their age must be greater than 50, they'd be making a lot of mistakes. A lot of people 50 and under can legally drink, but they would predict that they can't. If they guess 40, they're making less mistakes, and if they guess 60, they're making more mistakes. So one process they can follow is to make a guess and then adjust the guess in a way that reduces the number of mistakes. For example, let's say they start with 50. If they look at how many mistakes are made by guessing 55 and 45, they see that setting their guess of the legal drinking age to 45 is an improvement. So they adjust their guess. Now they try 40 and 50. 40 is an improvement. Repeating this a few times, eventually we get to 20. 15 and 25 aren't improvements, so they reduce the size of the adjustment from plus or minus 5 years to say plus or minus 1 year. They look at 19 and 21 and realize 21 is an improvement, and they can stop there. This is how neural networks learn by example, repeatedly correcting their guess to better align with the data. And this is what most lectures on neural networks will teach you. But I want to show you a different perspective, one that will make the drawbacks and pitfalls of neural networks more apparent. Instead of repeatedly changing our guess to better fit the data, we can see this as a process that repeatedly changes our data to better fit the guess. For example, let's say my guess of the threshold that distinguishes people who can legally drink from those who can't is 0, which obviously doesn't work well. But we can shift our data to better align with this guess. Notice that if we take all the ages and subtract 5 years, we get a bit of an improvement in the number of mistakes made by our guess. If we keep doing this, we can shift our data so that it's properly centered around 0, and all people who can't legally drink are on the left side of 0, and all people who can are on the right side. 21 is the number of years by which we need to shift the data in order for it to be properly centered around our guess of 0. And this perspective is a much more accurate representation of what neural networks are actually doing. They have a standardized guess, and the goal of the neural network is to figure out how to warp the data toward that guess. We can break up this process into a few key pieces, which we can capture in a diagram. This first circle is the raw data, in this case age, which flows into the next circle where the data is warped to be shifted by 21 years, for example. The warped data is then evaluated by the final circle, which is our guess that the warped age is greater than 0. In order for the green circle to know exactly how to warp the data, we need the red circle to communicate back the number of mistakes made via a feedback loop. And at a high level, this is a neural network. In practice, you'll have more than just age. You could have study time, exam length, household income, etc. From these, we want our neural network to extract hidden factors like GPA, which we forgot about. So we warp the data in multiple ways, hoping that one of these will discover the particular combination of factors that equates to GPA. Let's go through this one step at a time. At first, we have a bunch of data. Some factors may or may not be relevant to the task. In this case, let's say the task is to predict whether a student will pass or fail an exam. We feed our data into the neural network, which is then warped by various mathematical operations, think adding, subtracting, shifting of the original factors. The hope is that this will uncover hidden factors which are relevant to the task, like GPA for example. Finally, we use all these hidden factors to make a guess. Through our feedback loop, we can evaluate just how many mistakes are made by the current configuration. Did we shift too much, too little, etc. We can then make adjustments to how exactly the data is warped so we can make less mistakes the next time around. We can think of each of these circles in green as little workers with a task to warp the data in unique and fun ways. Making adjustments is a bit more complex now because we have to consider how much each worker contributed toward the mistake. So each worker gets varying levels of adjustments. At each step in this process, we hope to make less and less mistakes. Sometimes, though, the path to doing the best job isn't always so straightforward. You can't fix a house into becoming a mansion. At some point, you need to tear down the house and build something new, temporarily creating the worst possible living situation, a construction site. This is a big blind spot of neural networks. They always try to reach their goal through constant improvement. But this may not always lead to the best outcome. And while this may be intuitively easy to understand, finding the best outcome in a reasonable amount of time is so far an unsolved problem. I like the worker analogy because you can think of this neural network as a bunch of individual parts working together toward a common goal. Most of machine learning now is finding different ways to organize these workers so they work together in different ways toward different goals. For example, we can have lots of layers of workers and lots of different kinds of relationships between workers. It gets overwhelming real fast. Let's quickly recap and then talk about some of the drawbacks and limitations. Neural networks are a mathematical process. They warp the original factors in different ways in the hopes of finding hidden factors more relevant to the task. They iteratively guess and adjust the warping based on the mistakes made. One of the biggest drawbacks of neural networks is that what exactly these workers learn is not very clear. Untangling the data that has been fed through this network to understand exactly what these hidden factors are is practically impossible. Since these are just mathematical transformations of our data, it's not really clear what study time plus 4 times exam length minus household income, etc. actually means. But beyond interpretability, there's transparency and ethical considerations. In the same way that GPA was hidden in a combination of factors, what kind of racial or ethnic information could be hidden? For example, consider building a hiring tool to evaluate candidates. What combination of factors could equate to racial or ethnic information, creating a biased or discriminatory model? Sadly, we just don't know until it's too late. Sometimes, these neural networks learn hidden factors we don't expect. For example, if we build a neural network to distinguish planes from cars, most likely the hidden factor most relevant to the task will be the background color. Most pictures of planes have the sky in the background, which is blue, and most pictures of cars have roads and cities in the background, which are gray. So the neural network won't really learn the difference between a plane and a car, it will just pick up on the easiest way to distinguish the two sets of pictures. And maybe the most important thing to keep in mind is that the barrier for entry for using these very powerful predictive tools has been significantly lowered. It used to be you needed deep statistical knowledge, domain expertise, and years of study to understand how certain factors influence a particular outcome. Now, we've opened the door to using these tools in ways that are totally insensible and nonsensical. Here's an example of researchers in 2016 who tried to build a neural network to determine from a person's face whether they're a criminal. The neural network has good accuracy, but you have to ask yourself, does a person's face really determine whether they're a criminal? No, of course not. But neural network don't know. Neural network just do. I hope this helped you better understand neural networks, their limitations, and pitfalls. Leave a like, subscribe, and help me share this knowledge around if you found it helpful.